Hello and welcome everyone to episode 6 of Talking Shop with Tony Abbey. My name is David Quinn, editor of NAFEMS Benchmark magazine, and I'll be your host for today. This series is part of the wider NAFEMS community programme of online events that we are delighted to be bringing you. You can see more details on the NAFEMS website and hopefully find something else of interest as well. This week we're looking at high cycle or low cycle fatigue. What's the difference? We'll kick off, as usual, with a 30-minute presentation from Tony, then open things up to your questions and comments. You can submit your questions by using the Q&A box, which is accessed via the cartoon question mark to the right of your screen. We will then go through a selection of those questions at the end of the session. So without wasting any more of your time, I'll hand you over to Tony.
Thank you very much, David, and welcome everybody to session 6, high cycle, low cycle fatigue. What's the difference? Is it just a number? Again, just to mention for those of you that we had a little bit of a bandwidth issue with our last presentation, which was on, gosh, I've even forgotten what the title of that was now. Can you remind me, David? What was that talking about?
It was buckling, wasn't it?
Yeah, nonlinear buckling. It's one of my, I don't know why I forgot, senior moment. It's one of my kind of favorite topics. I thought there was a lot in it. I apologize, bandwidth kind of messed things up. For those of you interested, I've redone the video recording completely from scratch. I've also able to take all of the text Q&As come in, cut and paste those, and actually do a little bit more of a curated kind of answer to them. So I was able to link back to some of the slides, do a little bit of kind of animation over the top of it. So I've split that up into 2 videos, the presentation and also the Q&A. So for those of you who missed it, please go to either David's website, go to NAFEMS website, go to www.afetraining.net, look at any of our posts, our information. If you can't get to those videos, please feel free to send me an email and we will point you towards that direction. Anyway, starting this week proper, session 6, high cycle, low cycle fatigue. What's the difference? Is it just a number? That's really the idea. Quick little bit background on fatigue analysis. We all know it's about cycling. So here's like a paperclip, which we're going to, maybe if you're bored listening to me, you're just going to wang around this paperclip and it's going to fatigue at some point. So the idea is this is a cyclic load. And if we say that the force is proportional to the stress, that's the basic idea of uni axial type of loading. It's related back to testing where we have a uni axial specimen where the force is proportional to the local stress. Now we can have a stress concentration factor in here, geometric concentration factor, maybe due to the curvature here. But basically there's something causing that fatigue to start. And if we kind of zoom in electron microscope to this little region in here, the idea is the surface of our component, whatever it has little pits which are just due to normal manufacturing, just due to normal kind of material defects. And the idea is for fatigue analysis, we're talking about these pits, these local sites tend to grow, they tend to coalesce. They get to a stage where we're about to start to produce a crack. Fatigue analysis is rather curious. Strictly speaking, it's about the life to initiation, not the life to actually crack and final failure. That's sometimes a little bit difficult to kind of accept that. High cycle fatigue, where we're going to talk about, is certainly that kind of issue. The idea is the actual time spent cracking and actual propagating is tiny compared to the initiation part. So our fatigue life is really fatigue life to initiation. There's a big gray area, that's another big subject, but that's basically the idea we're going to start to talk about. And our stress level here is a low stress level, highlighted here. Typical stress amplitude we're talking about, we'd see, so that nominal stress times the stress concentration factor is typically going to be well below a value required to cause a static overload. And that's really the key thing to fatigue. That being the case, we're talking about low levels of stresses, high levels of fatigue. That's typically what we think of high cycle fatigue. This is a snapshot of a cotter pin. The initiation started down in here. We can't really see that initiation site. Go to electron microscope, maybe we can actually see that going there. And the black area is the oxidization or rubbing as we're actually starting to propagate the crack. From an analytical point of view, fatigue analysis is about finding that initiation point where that's likely to reach that kind of perfect storm. the actual propagation is fracture mechanics, which is a different topic, which I'll probably talk about some other week. And then we reach the edge here, where we just reach an overload situation. So at some point, brittle fracture, fast fracture, and that's a static failure. So there's really three phases. We're talking about phase one, which is the initiation stage, and two approaches to that initiation stage, low cycle and high cycle. So there's a kind of a lot to kind of think about the way that we actually separate these things out. So fatigue is cited as being one of the major causes of in-service failure, associated very much with rotating machinery. So as soon as the Industrial Revolution came along, we've got pumps, textiles, machinery, looms, and so on. People started to find failures at unusually early levels. So typical railway axle failures were due to typical ore trucks in the early days, carrying ore from A to B. They'd take their truck, the design of a truck, they'd stack it full of ore, really, really overload it, and say, well, look, it's surviving. What's the problem? This is going to be okay. 3 or 4 months of trundling up and down a track, suddenly at half a load, the thing fails, the axles fail. So that sort of prompted a lot of experiment, a lot of evaluation into what's going on, particularly railway axles, mining equipment, and so on. Going back to like 1840, 1860, 1870, something strange is going on. And somebody came up with the term fatigue, meaning basically the material just gets tired. They had no idea what the mechanism was, just basically the material is getting tired compared to our static loading. And a lot of that early type of experimental work has really taken us through to the 1920s to really, that's been the basis, just really observation, comparison against test. No deep level kind of micromechanical type of approach, as we'll see a little bit later on. At 1948, I'm going to show you a film poster where they're still assuming something magical is kind of going on there. So we know that we've got this cyclic behavior. Volo was, I think, commissioned by the railways or was a railway engineer, and basically he said, let's look at experiments. He took axles, put different weights on the axles so we have a different stress amplitude, and then he actually plotted the number of cycles to failure, just rotating cycles to failure in this particular case. He was able to come up with a curve, which is our SN curve, which has stood us in good stead pretty well since about 1850, 1860. We don't know necessarily why it fails. Imagine this a scatter of data, so I just want to really emphasize this. It isn't really a straight line. I want to get my narrow pen here. Got the pencil tool. So we've got a cloud of data sitting around here. Imagine this is data points, and we're doing our best fit through here. Sometimes people think our experimental evidence just shows a nice straight line. It doesn't. It's a curve fit through there. But either way, we get our straight line through here, and that's a straight line drawn on a log-log scale. Log-log scale is very important because it means our stress is very sensitive. Small changes in stress, big changes in life due to the fact it's on log-log scale. Nevertheless, this Volo curve is a fundamental SN curve saying if I know my stress amplitude, I can look that up and I can get a prediction of big N is the total number of cycles to failure. Now, the number of cycles to failure is not dependent on time, like wall clock time. It's dependent on number of cycles. So I have something such as, say, ground-air-ground cycle event of an aircraft maybe happening every 8 hours, pressurization, depressurization, that's one cycle. My aircraft hopefully is going to last 30 years, so that's a long life. I get something like a railway axle, maybe I've got to replace that maybe every 2 years or whatever it might be. Some things get even higher usage. If we get too fast a usage, then we may be thinking about dynamic effects. We have to go to vibration fatigue because there are dynamic effects coming in. So it's basically we can have something happens fast. The fastest cycling I've ever seen is due to gunfire in a combat aircraft. Very, very heavy cycles coming through, amplitudes coming through to a piece of electronic equipment nearby. And the total duration of the gunfire of the life of that aircraft was around about 5 minutes. So you can see you've got a fatigue life of 5 minutes, but under a very, very aggressive time scale, as opposed to maybe 40 or 50 years for other things. There's the cycles that count, and the stress level is going to be a stress level we said is going to be well below yield in that particular case. So we can have, this is the area we're interested in, And now we've got to draw that line, and we typically talk about stress amplitude. And now we can actually talk about, this is 1,000 cycles to failure, and we're going to see we can come up with a value here experimentally. This is typically 10 to 6 or 10 to 7 cycles to failure. There's sometimes a notch in the curve here, or a change in the curve for steels. Polished specimens show this. Other things such as aluminium show a curve coming down. We use 10 to the 6 or 10 to 7 as like a datum or yardstick. Steel polished specimen, we could actually get a stress level below which there is actually no fatigue. That's called the endurance level. We tend to use that 10 to 6, 10 to 7 just again as a datum point. So we're actually coming up with two kind of data points. We're coming up with a data point which is somewhere up here, which is going to be associated with yield, and then some point down here which is going to be a low level of stress. So those are the two ranges of stress which we're drawing the graph at, which is perhaps a little bit confusing. This is SN, high cycle fatigue graph, and now we've got an interception point which is actually to have a very, very high stress level. So this is the SN curve. If we don't have data, and the two sets of data, I don't know if I put them on this graph here, I haven't put them on there yet. We need to have two sets of data there to describe the curve. If we haven't got that data, what we can do is take a bit of a flyer. We can take ultimate stress, which is above yield. Typically, some say 1.4 to 1.6 times yield. Say take 0.9 of that, and that's given us our point there, bang. Well, that's already laid some suspicion in our mind in the sense, well, I thought you said that has to be an elastic limit in there. So there we go, and bang, straight through that. It's really to give us a datum point there. Datum point there is usually low stress. So that's kind of raising doubts in our mind. Now, there's all sorts of different values you could use here. Maybe the questions are going to say, I'm going to use 0.8, 0.7, I use this reference, I use that reference. That's very much a kind of empirical kind of value, as is the 0.5 times ultimate here, but it does mean given any material, and I even push these to be substrates for PC printed circuit boards and so on. As a flyer, as a getting into the game, I will actually set up my data using this kind of approach. The question mark here is, I thought you said low stresses, which are not going to cause failure, and now you're giving me a stress which is definitely going to cause failure. So that's really what we're going to talk about, how we kind of reconcile that fact there. So this is the two coefficients we need to use. You can draw this on log paper, which we used to do in the old days. These days it's going to be programmed in, and this is the expression. We've got a coefficient, which is the fatigue strength coefficient. That's some fundamental data you've got to test for. You're going to be fitting through lots of data to try and find that. And then the slope of the curve, the strength coefficient, again, you're going to be testing for that. So you hope to get values for C and B. If not, you can use the 0.9, 0.5 trick. Watch out to see what your preprocessor is going to tell you you're doing there. But that's basically our rule, what we base everything on. Remember, this is all going back to experimental evidence. We start with Uni Axial test of smooth, polished specimens, and then we're going to degrade them in different ways. We can put notches in. We can actually put different forms of machining in. And these are going to be knockdown factors, typically on this value here, which is going to be the S 10 to the 6 value. So what I'm going to say is, in the presence of machining, surface finish effects and so on, I'm going to push that down, which is going to be shorten the life. Notice that typically, very often, I don't mess around very much with this area up in here, because I'm assuming that's governed by yield failure. In other words, like a static failure. This is more for kind of fatigue prone. So again, that's another little clue, the way that we're going to be. And modifiers, which are very, very important, going to be typically applied at that end. And those modifiers can be very important. Just again, a little bit of an aside, I can do my stress calculations, I can come up with a linear FE analysis, do a mesh convergence study, get a stress at a particular point. That well could be dominated by actual service terms I use, my correction factors due to corrosion, due to different forms of machining, different metallic structures, whatever it might be. That might be more important than actually getting an accurate calculation. We want to get an accurate FEA calculation But if we don't put real life factors on there based on experimental evidence, then we're kind of fooling ourselves there. So we've now got the stage where I've kind of gone ahead and sketched this on. Whoa, what's happening to the slides here? So we're on that slide, and basically we're saying we want to be able to get, this is our area. Not sure what's happening. My slides are kind of jumping around all over the place. Are you seeing that at your end, David? Okay.
You're on slide 8 at the moment, and I can see your pointer.
Okay, it's just probably something's happening at my end. I don't know why. So the question now is, we've got stresses which are fluctuating in nature. We want to look at we've talked about loading should be low enough to have many cycles to cause failure. One of our questions is, how high is high, how low is low? And when we talk about high cycle fatigue as opposed to low cycle fatigue, how high is high? Well, I've seen various numbers which have been created. And this is my little Hollywood caption. There was a guy called Neville Shute, who was actually a very, very good engineer. He decided to stop being an engineer and write books, which is probably a very sensible thing to do. He wrote a book, and Hollywood picked it up in the late 40s and turned it into this dramatic-looking film. And the punchline of the film was, there's an aircraft that flew, reached 1440 hours, had a failure, crashed, and burned. He was on aircraft number 2, which was going to join the fleet, and he'd done his calculations and decided that, 1444 was where this particular aircraft was going to fail. Now, he didn't really know what fatigue damage, what actually caused it. He could understand, and we're looking at graphs, as we've seen, to actually predict fatigue life, but basically, what's the mechanism of fatigue life? Now, this is about 1948, and he was taking a bit of a flyer. Nobody has really actually figured out at that stage what's actually causing fatigue. He had all sorts of strange ideas, a little bit metaphysical kind of ideas. Nevertheless, he turned it into a good story. He talked about fluctuation of the tail causing failure, and this was before the comet disasters, probably about 3 or 4 years before the comet disasters, where we know pressurization would cause the issue. But basically the point was, it's a very low cycle fatigue, and he's able to predict within a few hours. To be a plot spoiler, he basically didn't want the aircraft to fly that he was on and his friends were on or whatever, and he basically pulled up the undercarriage lever and crippled the aircraft so it couldn't fly. They actually put it back into service, flew it for a few hours, and said, well, what's the problem? He said, well, I made a slight mistake in my calculation of temperatures, so it's actually going to fail not at 1440, but at 1453. And at 1453, they put it on test and it failed. We can't get that level of accuracy. It is Hollywood. It's like an early worker, and he actually worked at the Royal Aircraft Establishment, but he was taking a guess, a little bit of you could say, poetic license about that. So this would be very low cycle fatigue, something going on here which is not our typical low level of stress level, something which is a higher level of stress level, which is causing that problem. I went a quick survey through textbooks and reports and so on to say, what is the definition of the transition from low cycle to high cycle? And I had all sorts of numbers, down to 1,000. So if you get below 1,000, then you should be considering what we call low cycle fatigue, and we'll get into that shortly. And I've had all the way up to 100,000. I tend to think of somewhere about 50,000. I look at a report and say, if you've used a high cycle fatigue approach, you got 50,000. I want to look a little bit more carefully at the work you've done. And the key thing is I want to look at the work you've done, because basically what is going to actually cause a transition, it's not a number, it's not something that somebody has figured out. It is actually going to be our definition of what we assume is going on. Now, for some reason, my screen is kind of going nuts here. I'm trying to get full screen so I can read what I'm saying. But basically, plasticity, fatigue plasticity, see if I can swap to another screen over here. It's all about plasticity. High cycle fatigue assumes no plasticity effects. And because local stress and strain are proportional to nominal stress for uniaxial loading, and we might use a stress concentration factor, just a geometric factor that's simplest, we can actually say we can use elastic stress and strains. And down in the kind of the area I've drawn down in here, down in brown, then we're okay. We can assume our stresses are low enough so we can actually take this assumption into place that our stresses remain elastic. But we saw here at S1000, hey, hang on a minute, we're taking 0.9 of ultimate. Isn't that violating what we said? We're taking 0.9 of ultimate. How can that satisfy a linear response? Well, it can't. In fact, the elastic stress prediction could be even bigger than a stress of ultimate. What we're doing is the real material is going to go up this pecked blue curve. If we run a linear analysis, as many of us have seen, if we just overshoot, we get into realms of ridiculous levels of stress. So nominal times stress concentration factor can take us up here, which is a complete nonsense, and that cannot be fitting into any rationalized SN curve. This point out in here is really a datum point we use to extrapolate the curve. We've got a nice linear curve in here, but we're really focusing our high cycle fatigue calculations are done down here. This is just a point out here so we can kind of draw the line, but we're actually going to be doing the calculations down in here where going up and down this part of the curve is valid. Over in here, going up and down that part of the curve is a nonsense, and you can see 0.9 of ultimate, we're not going to be linear, we're going to be somewhere up in here. And if we ran a linear static analysis and didn't do any correction of what we are doing, for fatigue analysis, we're running linear static. And we're saying, well, hang on, we've got a stress which is a crazy stress up in here. But if that's the case, then we have to take some other approach to that. And that approach we're going to take is to basically say, let's use a strain-based approach, and we can use a strain life type approach. If we use a strain life approach, we can go up that nonlinear stress strain curve. So basically, we can go up here and calculate our fatigue, not going up here and have a ridiculous kind of level of fatigue. So that transition really is given by, do we have, can we assume that we have proportional stress to strain, so we're in the elastic part, or do we need to bring in our plasticity? And if we do, we use a strain life approach. The reason for using strains is that we can actually work with strains because we can separate plastic strains from elastic strains, as I'll try and explain on the next slide in here. So basically what we can say is we've got a local feature in here. We're going to use an elastic and a linear elastic analysis. We're going to recover a point in here, but we're going to do something about that point and convert it into a local elastic point, a local elastic plastic point using Neuber's correction theory. Now, Neuber's theory assumes it's a local tiny region around that inclusion that we're talking about, which is going to be growing. It's not a big region of plasticity. It's a very local region of plasticity. And if it's occurring locally, and it's surrounded by its material which is surrounding it, it's the material around it which is actually driving that behavior. It's not a load controlled, it's a strain controlled. If it's strain controlled, like a displacement controlled, as for example, we got some softening in the material here, that's okay, we don't get a runaway. So we can actually relate that to a strain-controlled specimen where it's displacement or strain-controlled. So as we start to soften, you'll understand the softening. It won't just suddenly rapidly run away and break as if we do a force-controlled. So we have a good analogy between a smooth specimen, which we can actually use a strain-controlled approach to look at a strain-based life, as opposed to a stress-based life, which we've been using up to this point. And that's basically the idea. So small amounts of strain, very locally controlled, their growth and their behavior is controlled by the surrounding elastic material. And that's the breakthrough. And that's the real transition from high cycle to low cycle fatigue. It's not a number, it's the presence of plasticity. Now, a very quick review of plasticity. We've got our local, our elastic response limit here. We reach a yield stress. We have a bilinear approach. We could say we use a tangent modulus, and we just simplify that. We reach the limit of our loading. We unload, and we get down to some locked-in residual plasticity. But in fatigue, we're interested in reverse loading. So we reverse load, and at reverse load, where do we go plastic? Well, if we assume a kinematic approach, we can just say whatever yield stress we reached here, we reach twice yield stress in here, and then we go, and that's now our elastic reverse loading. If it's isotropic, we say, well, we reach that stress limit there. Iso means equal. We take just a reflection here. Whatever stress we got there, we get the stress down there. And so we actually will go and yield at a different point. Now, what model we would use, we typically would probably use kinematic loading in our typical fatigue analysis, but we could use either of those. It's material dependent. It's also dependent on whether we, the directionality of the stress and so on. But this could be one kind of approach. Now, for cyclic loading, we want to know what's going on there. So that's one of the things we need to understand. Now, we're actually going to put in a continuous material curve. We don't want to put a bilinear curve in. We could do, but a continuous curve is easier to work with. Notice as we come up here, we reach the limit, we unload, and this is kinematic unloading, and we've got a load back down in here. Now, we're not interested in the stress range. The nominal stress range, if you remember, was some stress which we applied, say nominal stress times the stress contraction factor. That's not the stress we get there. This is our local point stress strain curve. So one of the issues is where do we reach that? We can also see that we're including the plastic part. This is the residual plastic stress. We've got the elastic part. We've always got an elastic component playing a role, but we've got ever-increasing amounts of plasticity. So that's what we want to bring in, at least locally. So sometimes we call it the strain life approach, we call it the EN approach, we call it the low cycle approach. We're saying linearity is just limited to this level. SN type approaches, high cycle fatigue is limited to this approach. We want to get over to this point in here because we want to deal with that presence of that plasticity. Now, we need to change our terminology, and this is a bit of a pain. Basically, this is the stress amplitude. We would say take the stress range, we divide by 2. So we can talk about a stress range. A reversal is basically half a cycle. You think, well, why do we want to split a cycle up into the up and the down, or the up and the back, if you like? Well, the reason is later on, as we get more sophisticated with cycle counting, we might want to take that half load upload and a different download and kind of combine together and come up with a synthetic kind of description of cycle counting. So I think that's the reason we kind of split it into that. So if we use the elastic SN relationship, which was amplitude and cycles, can you see that that's just the strain range divided by 2 is our amplitude, and twice the number of reversals is just our cycle. So that's what we saw before. We've got the 2 unknowns, the coefficient and the exponent. That's just the SN approach. So it's just the SN approach cast in a different way. Now, the breakthrough was that Coffin and Manson and other workers said, if we go for low cycle fatigue, where plasticity is clearly present, let's mathematically take out the plasticity and see what happens. And lo and behold, if we take out the plasticity, we end up with, I haven't drawn it, but basically we've got a stress strain curve. I'm sorry, we've got a load versus life curve, where we can actually draw strain amplitude or strain range, if we like, and we've got yet another linear curve in log-log space, and we can actually look at the number of cycles to failure down in here. But that relationship is the plastic strain. So that would require a little bit of processing. They did that, and they took out and said the plastic bit related to the life to failure. If we could actually come in and work with that, then we've got a prediction of our life. But that's a real pain. You've got to go in and produce plastic strain only. So that's kind of like half the story. Now this is why it's recast in terms of strain, because we're talking about a strain amplitude, number of cycles. You can think of it as like an equivalent to SN, but it's basically going to be just plastic strain on its own. So that's going to be half the story. There's 2 more coefficients needed, or 2 more terms needed. We need the coefficient, we need the exponent. These are going to be different from the SN curve. So we've got 2 curves, and we can actually basically bring them together. Let's bring the elastic part and the purely plastic part together. This is the work they did. Let's combine them together and say the strain amplitude, let's work with strains. is going to be equal to the elastic strain plus the plastic strain. Well, the elastic term is just, let's do a transformation and just say we can transform through the Young's modulus because the stress-strain relationship is a linear stress-strain relationship. So this is a heavily disguised SN curve. That's all we've got. Now, the plastic term sits on there. That's the one we figured out. That's got the new relationship. So we're going to take the elastic term plus the plastic term, add them together, and now in terms of the strain range or strain amplitude, we can choose either. The strain range is here, and it's got the elastic part plus the plastic part. We can look at that and say this gives, again, we've got two coefficients to worry about in each term, or two unknowns in each term, got four unknowns to deal with. And now we've got a strain life curve. So if I know the strain range, divide that by 2, I've got the strain amplitude. Now I can go and predict the life. So this is to put the correction in for the plasticity, and this is the essential low cycle fatigue type approach we're going to be using. And this is the total graph. There's the elastic part, so down in here all I need is the elastic relationship and I'm good to go. And you can see here just an elastic stress strain curve in here. There's no nonlinearity. Then I've got the influence of plasticity coming in here. So this is like the gray area. Maybe I could get away with this if I just did a high cycle fatigue. We get down to here, the presence of plasticity is so dominating, I get up here, I better be using the combined curve. So there's the combined curve. I've drawn some hysteresis loops. The one over this side just stays flat. It's just the elastic part. We could get away with an SN approach. Over here, the big dumpy fat hysteresis loop, the volume underneath there means the actual dissipation due to plasticity per cycle. So the bigger, the dumpier, the kind of the area underneath there, the more plasticity I have. And you can sense that. Here we didn't even go plastic. Here we've gone plastic. There's a lot of plasticity. And somewhere in the middle here, there's a little bit of plasticity. So one of our jobs is to create these hysteresis loops. And what we're really interested in is not the nominal stress anymore. It's that stress range. Divide that by 2, gives us the stress amplitude. And that's what we're going to be using in this particular curve to look up the life. So if I've got a particular cycle, I can come in on a number of cycles. I can say there's the, let's say there's the strain range. There's my number of cycles to failure. And that's going to be including the plastic effects. So if I've got plasticity, I've got very high levels of stress, then that's okay. So up in here, I could actually have a very short life, and that could be the order of, say, 500 or 600 cycles, and that's okay because there's a large amount of plasticity associated with that. I've taken care of that. So it's not a number transition, it's actually a material behavior transition. It's the presence of plasticity. Now again, as I said, I can actually draw a stress strain curve. This is a simplistic bilinear approach. I can either draw the tangent modulus, which is the change in stress with total plasticity, or I can have the plastic modulus, which is the change in stress with just the plastic strain. Or I can put that all together and I can say, let's create a power law. And the power law is useful because then it's going to be, a plasticity will be a continuous slope, which might fit our data better. And again, I've got 2 more coefficients to deal with, the strain hardening coefficient and the strain hardening exponent. So I've got a way I can actually mathematically draw that curve and deal with that. So that's the approach that we take in there. So that's our material law will be given by that particular stress strain curve. Now what I've done here is to plot the elastic part, and don't forget elasticity doesn't go away. Elasticity is still present as we reach the plastic limit, but it's just a small contribution. The big contribution, the big plastic slip occurring now is this is the power law associated with that. We add the 2 together, and this is the blue curve, is the true stress strain curve that we want to deal with. Now our problem is we're applying a nominal stress, perhaps times its stress concentration factor. Where does that take us? How far up here do we go? We've got to have some way of saying that. We've got kind of like macro level stresses, simple stress definition. Somewhere locally in our hotspot, we've got this going on. And this is what we assume. Now we've got to go from our elastic response and transition to our plastic response locally. We're not going to run a nonlinear elastic analysis, Got to have some way of fitting that through that. And that's thanks to Neuber. Neuber came up with the idea, well, let's say we know that we're dealing with engineering stress, not true stress. Got a stress concentration factor. And Neuber said, let's think about that stress concentration factor. Let's think about the typical stress concentration factor, which is the change in stress as we increase that's the change in local stress as we increase the nominal stress. And then we can also think about a strain concentration. What's the change in local strain as we apply that nominal stress or the nominal strain? Now, below yield, they're both equal to KT because there's a straight relationship between stress and strain, so they're the same number. Big deal. Above yield, an interesting thing happens. So above yield, the strain concentration accelerates like crazy. You get a lot of strain, rapid increase in strain. It's almost like chewing gum. We start to get that strain starts to grow. Our stress actually drops off. It actually drops because we're work hardening and we get that reduction in stress. So one goes up, one goes down. So what Neuber said is let's multiply the two together and we get this term KT squared. Below yield is just KT. Take the square root of it, we're back to KT. Now we're getting the two effects combined. So he combined them together, and I won't go through the equations there. You can actually derive the equations. But basically, the work done on one side, stress times strain, our local response is equal to our, if you like, our global applied load, which is our nominal stress times the stress concentration. That's our elastic stress we have at that region. And then the local plastic stress we have there is related in this way. And there's the Young's modulus there. So everything on the right-hand side, we can actually calculate based on the knowledge of the general load level that we apply. The interesting terms on the left-hand side, that's what's actually happening locally. So those two terms, the stress and the strain, are the limits we reach on our nonlinear curve as we apply just our simple definition of our nominal stress times the stress concentration factor. So that's the magic of the Neuber approach, just very locally. Now, one of the justifications is, well, the area underneath this is the work done. If we just said it's a linear and we just keep on extrapolating linear, we know that's a crazy term, but that gives us a certain amount of energy done. We've actually got a change in curve here as we go up the real stress strain curve. The area underneath them is a similar kind of area. So you can work it on a kind of an energy balance type approach. The energy associated with both these methods is the same kind of energy, but we've broken down that stress and strain into that local kind of behavior. Now, armed with that little expression, that for a particular given stress state that we're interested in, we've got a curve which is based on here. This is our stress, this is our strain. We can write that down in terms of a curve here. That's called the Neuber notch term, and basically that gives us a curve in here. Where that intercepts our material curve, that's the point, that's the limit of our loading, and it's dictated by the actual stress level that we apply and our stress concentration factor. That's like our macro or our global type of application. That's our FEA result, elastic result. And then buried in there is we don't model the plasticity, but assuming a local presence of plasticity, that's the actual stress level and particularly strain level that we reach. And that's what we can get a handle on to include the plasticity and include these nonlinear effects. Now, getting that balance is quite tricky. In the programs I've written, I use an optimization approach to say minimize the difference between that expression, at what level of true stress, true strain do those two equations balance. So there are other ways of doing that. So we've got an example here, and at that particular load level, I match a particular textbook example. I've got a stress concentration factor of 2.42. There's my nominal stress. That takes me straight through yield, but then I use the notch term to say what's the equivalent strain amplitude and stress range, and then that gives me a true value I can use in my EN type of curve. So armed with that, I can come through and say, there's my first point. So I've gone up my stress strain curve and I've reached that first point there. That's given me a stress value and a strain value. They're not nominal stresses, not nominal strains. They're that local elastic plastic response. But I've still only run a linear analysis to get to that point. Now I've got to figure out how do I unload and go back to that point. And there's a little bit of a kind of additional issue there, and that's called the massing rule. The massing rule says as you unload or reverse load, you don't go up the original the original material curve. You actually double the plastic term. Now there is a geometric reason for that, and I've actually got a YouTube video which actually explains that kind of graphically. You always get this double curve in here. So we actually start with that curve takes us into the pattern, and then there's a double curve takes us back out again. This is kind of like if you got to do this as like a paper study, and in the old days we'd actually take our paper, we'd draw a double curve, and then we'd actually, believe it or not, we'd take tracing paper and draw over and say that's our hysteresis curve. There's the double plastic term in there. There's the factor of 2. It's called the massing hypothesis. You might want to do a Google search on that, or check out my YouTube video to find more detail on that. So now I've got this new material curve. This is the double curve. And again, I've got interception. There's my good old Neuber curve will be running across there. So this will be the Neuber intercept here. Where that intercepts my material curve, which is running through there, that's my second point. Now, armed with those 2 points, if I don't change the nominal stress state, I apply plus and minus the same, and then a reversal load. This is how I create my hysteresis curve, and that's what I want. And the key thing I'm interested in is my strain range. Take the strain range, which is elastic plus plastic, divide by 2, and I've got my strain amplitude. I can go and look that up on my EN curve, on my low cycle fatigue curve. So that's the big difference between them. And there I've got a strain range. I divide that by 2. I have a strain amplitude. I can look that up. I can look that up on a fatigue life curve, EN curve. There's my EN curve. I look that up, and somewhere over here, if I follow the, sorry, I've got to move that over so I can see it. You can probably already see it. And I think it's the book by Bannatyne, and I've worked through and I come up with pretty well exactly the same calculation there. If you join the fatigue course, and you're very welcome to, I think there's another one starts in about 3 months, actually provide an Excel spreadsheet calculator which goes through this process for you. So again, you can rewrite that or use it as given, but it will give you the value. So that is actually 2,000 cycles, which is definitely low cycle. If I saw that and somebody had run a high cycle fatigue, I'd think, okay, you're kidding me, because you've used this curve to try and give me a life over here somewhere, and I don't believe you, because there should have been a plasticity effect. So for me, somewhere below 50,000, I always get a little bit suspicious. I'm, again, an older suspicious character, so I don't use a number. I use the presence of plasticity. I'd literally look at that peak, the linear stress calculation that's being used for the analysis and see, are we close to yield? If we are, then I really want to see evidence that you've repeated that using a low cycle fatigue type of approach. So there are other extensions to that. If we've got a generally wider region of plasticity, we might actually use a nonlinear plastic analysis. Then the Neuber rule strictly breaks down. There are other variations on that, such as the Seeger methods, which you'd start with a nonlinear analysis and then approaches in there. Also, instead of KT, which is a straight geometric factor, times our nominal stress, there is actually sometimes an alleviation, because there's a little bit more going on than just a geometric factor. So then we use the notch factor in that particular case. So again, more details on that if you're interested in the full fatigue course. So I run a few cases. This is our case where we run with a load. We run up to a value and then reverse. And then you can see we're cycling then at that particular load level, and our hysteresis loop is over here. So basically, we've got fatigue life has dropped because we've actually got a mean stress that's been put in. We jump up to 50,000 psi. We go from 0 to 50 back to 0. So we've got a mean stress, and we got down to 1,000 reversals, 500 cycles. So very, very short fatigue life in that particular case. This is basically a whole series of results. So in here we've got, that's our fundamental stress-strain curve, nonlinear stress-strain curve. That's a very, we could get away with high cycle there, get away with high cycle there. There's not much evidence of plasticity going on. As we get to this level of loading, we've got more plasticity coming in. We get a dumpier shape in there, and here's an even bigger shape. So in each one of those cases, let's say we had like a minus damage rule, we'd add up the strain range there if we wanted, strain range there, strain range there, and strain range there, divide each one of those by 2. Each one of those would then look up an EN curve to get the behavior. We could get away probably with high cycle fatigue down in here. By the time we got over here, we definitely got to use a low cycle fatigue type of curve. And I've shown over here the different load levels. So we're going from 0 to max, down to 0 to max, and on and on and on and on as we go through the life. So these levels down here we might get away with. Levels up here, if we did a calculation just of the nominal stress times the stress concentration factor or the value coming from the epi analysis, we'd be way through yield and probably through ultimate there. So we've got to then backtrack and use this kind of approach in here. And I think I've nearly finished. Dave will be relieved to hear. And this is really like the summary sheet in here. If we're using the SN curve approach, down in here we're okay because we're operating up this part of the curve. So the linear assumption we make for the peak stress is okay. Move into this region, and then if we shoot up in here and use this term, nominal times KT, then we're kidding ourselves. The actual theory breaks down because if this is 0.9 times ultimate, and you've got a value of 3 times ultimate, how do you fit that back to the SN curve? You can't. So even if you have sort of like 0.9, 0.8, 0.7 times ultimate, it's still way too high. So anything beyond yield or approaching yield, we should be going up this curve, and that is basically the differences here. That won't be that line, and let's draw another line on there. That will be the EN curve line, which will look like, again, I've got to juggle around to get the picture in. Come on, WebEx, behave. And so the two curves would overlay, and there we have the dominance of that second curve, and then we have the total curve in there. So the total curve would be that total curve in there. So that's the idea. So to the left of the transition point, we definitely need to bring in that second term, kicks up this term completely, because otherwise we're up here, we're into fantasy land. So that's basically the idea behind the transition. It is not just a number, it's a different physics going on there. So that's the end of the presentation for today. I think our fingers crossed worked. We didn't get a dropout, thank goodness for that. So the video, I'll clean it up. We're going to have Q&A afterwards. I'll curate all those and put those up with the captions up as well. So look out for the link for when this video recording is just cleaned up and issued. Next session will be dates are rolling forward. I think I've got that right, next Friday. And I haven't told David yet, but the topic for next week is, I think, much a topical term, topology optimization, generative design. There's a tremendous amount of marketing stuff out there. I'm sorry, David. There's a lot of marketing stuff there. David's a marketing man, so just be very rude to him. There's a lot of stuff out there. Is it buzzwords? Is it reality? There's some strong physics behind there. There's some great engineering behind there. So we'll talk about that aspect next week. So I'll hand over to David. Having been rude to you, David, I'll hand over to you to take us into the next half.
No, that's fine. Thanks, Tony. As I say to many engineers who say the same, well, just tell me when you want me to stop marketing and I'll do it for you. That's fine. Thanks very much for the presentation, Tony. Excellent. We do have a few questions that have come in. I don't know if you can see those. I think the presentation went okay. Couldn't hear any dropouts at all. And as you were saying, Tony, I think the slide confusion was just at your end locally, because everything was fine here. So we're all good. But yep, there are a few questions there. Don't know if you can see them.
Yes. There's some questions about last week, and then coming into this week, there's a question from David. It says, "Hi Tony, thanks very much for the presentation. Let me ask, maybe I didn't just catch it. At stress life method, is the vertical axis S means the stress amplitude?" Yes, it is the stress amplitude, so we can work with stresses, and they are just basically the stresses coming straight from FE analysis. So if we're doing a hand calculation, there will be a nominal stress times KT. So we look that up in a textbook or some other method, and so we get our peak stress from a hand calculation way. From an FE analysis, it's the peak stress that we get directly from the FE analysis. So it's the elastic stress amplitude coming from our FE analysis. Badri has a question. Random vibration fatigue based on Miles' equation is linear. The assumption here is that the vibration fatigue is high cycle. What happens when the stresses are greater than yield? Is there a way to account for that? Yes, as I mentioned before, we basically it's the cycle count we're interested in high cycle fatigue, and also indeed for low cycle fatigue. So the rate of loading we don't take too much account of, but that breaks down if we actually have vibration fatigue, and that's where the dynamic effects, the inertia effects, come in. So it becomes a dynamic type of behavior. The assumption is that is high cycle. I don't have any experience with low cycle fatigue type approach with vibration fatigue. There probably is some theory out there somewhere, but I'm afraid, Badri, I will do a little bit of research to see if I find anything when I curate the questions, but there's nothing to my knowledge there. It's assumed to be a high cycle fatigue type of approach. Yeah, I'll leave it there, and then we may get into more there. Dieter asks the questions, typically elastic, plastic, and plastic sigma epsilon relationships have to be defined separately in the FEA software. That's correct. That's not always because of the starting point of 2% yield is not always defined. Can you elaborate on how to introduce this in software? We're based on a power law is the typical approach that we would take. That's the approach I've taken when I've written a MATLAB solution or I've written an Excel spreadsheet solution. That's how we define our nonlinear, as you say, elastic plastic sigma epsilon relationship. So the nonlinear stress strain relationship. There's no reason why you shouldn't use instead. You should use test data, so that would be a table data, or you could use a piecewise linear fit. So there are other forms that you could use to introduce that. I've used a power law. To do the Neuber intercept between the Neuber notch and the power law is easy from a mathematical point of view. Otherwise, there's lookup tables and other approaches. Again, if I get a chance on the curated video, then I'll try and expand a little bit further on that. Badri has the question, as per Neuber, we can do a low cycle fatigue without elastic plastic nonlinear analysis. That's the big breakthrough. The technique makes sense except for one point. Going back to the example you had written about design for strength or stiffness, if one member becomes plastic, the stiffness of the member also changes. Or is the assumption that local plasticity does not change the stiffness of the member? Sorry for the long question. No, it's a very good question. We're dealing with very small local regions of plasticity. So the idea is that the overall structure remains predominantly an elastic response. So there the idea that if you have a stiffer structure, it's attracting more load. That's generally true. We don't have big regions of local plasticity which are going to change the load path. So that is one of the limitations of the approach. We're talking about a local plastic correction, which is a very, very localized plastic correction. There are other extensions to deal with more, as I said, like the Seeger method, but even that, I think, is dealing with larger regions of local plasticity. To have something which is shaking down into a nonlinear response overall, I think, again, that's outside my experience for that. So as far as we're concerned, it's just this local, as you said, it's a local correction factor. How do we play the magic trick to go from an elastic linear analysis to form the basis of even our strain life approach it's that local behavior we're concerned with. Andreas has a question on page 21. Elastic plus plastic is combined together. Let's see if we can find page 21. Somewhere down in here. That's probably a quick way of doing that, but I don't know the quick way. Overshot it. Go back here. Which page 121, elastic plus plastic is added, yielding the blue sum of the curves. Which is below both? Not quite sure what you mean by the question there, Andreas. So the limit of yield limit is here where I've got the cursor now. So below that is our elastic response. And then above that is our plastic response. Maybe you can send me a separate email to expand on that, or certainly ask the question on LinkedIn there. Peter asks the question, which approach, low cycle or high cycle, would be appropriate for situations where there is a pretension present in the component which causes some local yielding. On top of the service load is added, causing alternating stress in those yielded spots. I have in the past run a nonlinear analysis so that the local region does see regions of local plasticity. And then I've taken a bit of a flyer. I've actually come up with techniques which are probably not very valid techniques, where I actually put the perturbation load and use the Neuber solution for the perturbation load. Now, there are better solutions for that. The Seeger method, which I don't have a great experience over, would be one approach we would use there. So in that particular case, we're starting from a nonlinear analysis where we got some local plasticity. And then small perturbations again on top of that. So I think that's the basis of the Seeger approach, and certainly the kind of hybrid approach that I use there, where I'm using the perturbation approach on top of the very local regions of plasticity. What is the effect of R ratio on the fatigue life? This is from Mr. Ali. R is basically giving us the ratio between the fully reversed. So R is -1, means we have, if I can draw, let me go to my sketch area. From bitter experience, it's better to have a clean sheet to start to draw these things. So what we've got is that fully reversed means that we have a fatigue life, which is a fatigue history, which is going from plus and minus load the same. So what happens here is that we can actually put a correction factor on. If we actually have the mean stress is not 0, we drop it down to here as we saw. So each case we're going from 0 stress to max. That's going to give us a different value of R, which is essentially associated with the mean stress level. There are correction factors we can use. There's two forms of correction factor we can use for a low cycle fatigue. And both of those, one operates purely on the elastic part, one is a combined part. So again, I can't remember the names. There's Smith, Watson, and Topper, and another one. So again, I haven't seen in a moment. So again, in the curated solution, I'll give you the two methods we can use there. Mike says, not directly related to the info in the presentation, but I understand the scatter factor accounts for the cloud of fatigue data versus discrete curve. It seems a lot of folks use a scatter factor of 4. Does the appropriate scatter factor work for a particular job? It's kind of combining two things together. Again, going to a fresh sheet. We've got an SN curve, and we assuming that that's been created. And again, remembering it's a log-log curve, there it is, but we've got a whole cloud of data, as you say, surrounding that. So we're actually doing the best bit through there. So do we take the mean curve is, say, 50% through there, or do we drop the curve down to so that we are at kind of the lower bound? So the worst, let's move it up a little bit. worst test data we'll ever find is at that lower bound. That's going to be incredibly conservative. So another way is to say, let's actually put a scatter factor. So the scatter factor is probably going to be at the high cycle fatigue end. We would be dropping this curve down to fit better. So again, we'd probably be using the endurance limit, or 10 to the 6 or 10 to the 7, to drop down in some way. There is another way of doing it, which is to actually put a percentage probability. So there's another equation, which again, if we get a chance, I'll post that up on the curated, which actually says, let's look at, instead of putting a scatter factor on, let's look at this as a distribution. So if we go across here, we could say, well, there's like a normal distribution, which I'll try hard to draw with my mouse. So that's going to be a distribution which should be an equal, let's get the right pen. So that should be like a, let's move that up halfway. So now I'm in good shape to draw a normal distribution. So I'm going to have to draw it and then move it. So a normal distribution is going to look, say, something like this. It's not a very good normal distribution, but something like that. Now I've got to try and move that. So, woo, the whole thing has disappeared on me. This is problems at my end. Sorry, I've lost my diagram here. Let's try and change the page and come back to that. There we go. Now I lost it again. So let me not touch anything. You won't believe how flaky it is at this end. So let's move the mouse completely away. Right, so no, this is nowhere near. I'm not going to move that curve in, because otherwise I'm spoil my picture. Imagine that binomial, that normal distribution, sitting over there. So 50% is the middle. So we can actually take, say 3 sigma or 2 sigma. So that's another way of approaching it. It's probably perhaps a better way of approaching it. When we do the QR, I'll kind of clean that up and do a better diagram on that. So a straight statistical approach is often a better way of doing that. And usually we have numbers and we have an equation, so we can kind of deal with that. Thanks for the explanation between low cycle and high cycle. Good. I'm glad it's resonating. It's always good to get some positive feedback. So, Steve, since the lower limit of high cycle fatigue is dependent on the presence of plasticity, is dependent on the material. One material might be 10,000 cycle, and one might be 100,000 cycle. A very, very good point indeed. So it's not a number, and you're absolutely right. There's more to it than that. We may have something which actually goes a much lower yield. And thinking about it, if we got pure shear, we got √3 times lower than that. So excellent point indeed there, Steve. Point I didn't mention. Oliver asked the question: is there a fundamental difference in assessing fatigue and shear and tension or compression, or is it just a case of using von Mises in all cases? That's a big question. If we got pure shear and we actually have shear SN curve, then we could deal with that. If we've got something which has shear and direct stress, but it's proportional, so we're just scaling that stress state up and down, that's called proportional, then we could use a signed von Mises, which we touched on briefly when we looked at the Moore circle. We could use a signed maximum principle. What we've got there is a combinational stress state. If we look at the stress vector through history of the cycle, the stress is swinging around all over the place. So there it's generally going to be used in a general combined stress state, so we kind of cheat. There are more, it's called multi-axial analysis. That's proportional. Full multi-axial is way beyond the scope of the half an hour here. It's probably going to be a PhD thesis in its own right. Oliver says, what are typical safety factors are applied to fatigue life in order to find a safe working life? Assuming a design in which once crack occurs, life to failure is very short. It's actually a bigger question than that. We could apply a safety factor, but we'd also got inspection coming in. We also got we've got a fail-safe approach, which means that if your critical part fails, there's another parallel approach. We also have a damage tolerance approach, which we bring in fracture mechanics to say, let's inspect this thing to make sure that it's okay. In other words, there's damage. Is it tolerant of that? So these days, maybe quite rare to have what we call a safe life approach, where everything is designed on just the SN curve. Yes, if you're not too worried about weight, and you've got happy to have a big margin, then you can apply a safety factor as you're applying there. But it is a kind of, there are better ways kind of approach it. But if you're not sure, and maybe it's not a life critical or mission critical, maybe we could take that kind of approach. Him asks, does the approach apply to viscoelastic, viscoplastic materials? I'm afraid I have no experience there. I will put you in touch with a guy there, and in the Q&A, I'll give a reference to guy William Mars. I hope William, if you're listening, I hope you don't object to that. Regarding stress approach, high cycle fatigue, which criteria are you considering for the stress? Mises, Tresca, max principle, or something else? I like to use maximum principle because, again, if my slides permit this, let's go to another work area, try and draw it very quick. Like a plate with a hole in it. There's my favorite example. What's the stress, which is elastic stress, which is governing it? It's going to be the maximum principal stress, which in our particular case, which is running tangential to that stress. In general, I'm thinking I've got a maximum principal stress. I align that with a fatigue crack and assume it's normal to that. I can't get any worse than that. Maybe my maximum principal is actually a slight angle off that. So we swing. Am I drawn that the right way around? I've got a crack going. Yeah, that's the right way around. So maybe the maximum principal is over here. I'd swing that around. This is for uni axial. For proportional loading, we're forced to use something like signed maximum principal or signed von Mises. But for uni axial, where we assume uniaxial, again, just to kind of emphasize, uniaxial is what all our test specimens are based on. So uniaxial means, as the name suggests, all our tests are based on loading, which looks something kind of like this. Again, WebEx is playing games here on my end. Uniaxial load all going in one direction. Proportional, we actually have a load, which is, say, doing this, but the load is always proportionally the same, so 2-to-1 ratio. Multi-axial, this does whatever it wants to do, this does whatever it wants to do, and man, we've got a continuously varying stress state in here. So those are the three levels: uniaxial, proportional, and multi-axial. So assuming your question's about uniaxial, then I'd always use maximum principle and assume that swing it around a little bit so it's aligned with the correct direction. I think maybe two more, David. Will that suit us? Okay, good. So last post too long. Does the not sure what you mean there. So this is coming from Mike. Does the appropriate safety factor for a particular job generally vary by material stress level, R or some other factor? No, R, the presence of a mean stress, we're going to turn that back into an equivalent stress. So I don't think R is such a big deal there, but certainly material is going to change the effect completely. Again, Amit, I'm afraid I don't go into, well, engineering plastics, glass fill polymers, and so on. As a first stab, I use the SN curve, 0.9 ultimate, half ultimate, and then my safety factor I put on there is a big one. Put a safety factor of 4 or 5 on that because I've got into the game. I've got some calculation of high cycle fatigue, but is it accurate or not? Until I get actually better material data, I don't know. So just to enable to do something, that's what I do there with a big safety factor. So for example, with printed circuit boards, things like that. Sandrine says some recent tests show that there is a drop after 10 to 7 cycles stress curve for steels and other metals after the endurance limit. How realistic is it to use the endurance limit? What we'd do then is we'd actually have an SN curve with 3 levels and actually just put 3 curves in there. So usually we get data to say this is what the slope looks like. If I've got good data to say what the slope looks like, then I'd use that data. So again, using a sketch, I'll try and, I promise this is the last question, David. So basically, what we said is we sometimes actually put a little lead in up to 1,000. You don't really need that. Then this is our main curve. This is what we're talking about down in here. Let's draw some axes in here. So this is our stress amplitude. This is our life. This is 1,000 value in here. So beyond here is really, it's going to be a very, very fast failure. This is our main thing in here. So the question is about, let me go back one slide and then again here. The question is, as soon as I kind of move my, it's like whack-a-mole. As soon as I move my thing over here, it kind of bounces around all over the place. That last slope, we can either assume it's horizontal, assume it's just a continuation of the main slope, or we have some data to tell us what that slope is. And again, we can make some assumptions, measuring assumptions, what we use half the slope, something like that. Again, remember, that's a very high cycle, 10 to the 9 cycles because it's a log scale. Are you going to be alive long enough to actually do a fatigue experiment of that? 10 to the 12 cycles. One of the problems is we've got accelerated methods, but again, there's not very much data up at that end there. So it's a little bit of a moot point. Yes, there are correction factors there. There's a bunch of other and other questions in here. I'll try and see if I get time to answer the QA there. I think the idea of splitting up into 2 videos is probably a good idea, David. What did you think of that method we had last time?
Yeah, absolutely. I think if there's the option to do that, if you wanted to do that, that would be absolutely fine.
Okay, so some folks can look at the presentation. Others want to dive into again, it's curated. I put the symbols up there. Sorry, the questions up there, so we can see what's going on. And I'll rapidly move back to your marketing slide. Here we go. Here we go. So, okay, thanks everybody. And I'll hand over David now to kind of wrap up the show for us.
No problem. Thanks very much, Tony. And thank you to everyone for attending today. As Tony said, the links to the video of today's session and the Q&A will be available on both fetraining.net and nafems.org over the next few days. You'll also be able to register for next Friday's session, Topology Optimization, Generative Design, Buzzwords or Reality. Those links will be live in the next few hours, actually. So you can get registered then. So hopefully we will see you back online next Friday. Until then, have a very good week. Stay safe, and we hope to see you soon. Goodbye for now.
So bye, everybody. And by next week, David, I'll teach you how to pronounce topology.
Tripped up. I had that beer about 10 minutes ago. That's the problem.
If you're not careful, put another buzzword over your little speech bubble over the video. Okay. Thanks very much, everybody. Yep.
Take care.